Good morning, everybody, and welcome to day 2. We will start this morning with different lectures on autonomy, cybernetics, robotics. So the first speaker will be Beate Kvamstad-Lervold from SINTEF Ocean. And she will present OceanLab and FjordLab, autonomy, ocean data, mapping, monitoring, what else? It's a title, it means that you can say almost everything.
Yes.
So please, Beate.
Thank you. Hi everyone, I'm Beate. Nice to see you all this morning. I'm a special advisor at SINTEF Ocean, and I'm involved in the development of what we call FjordLab. FjordLab is a part of Ocean Space Center. I do really hope that you have heard about Ocean Space Center, all of you. So I will not tell you about Ocean Space Center, but I will go more into details of FjordLab, which is one out of 8 laboratories in Ocean Space Center. And what is special about FjordLab is that this is a full-scale research infrastructure, meaning that this is instruments and sensors and equipment we are installing in the fjord and in the coast for full-scale research. The timeline in the development of FjordLab is shown on this slide. It will be developed in 3 phases. Phase 1 has already started. We received was granted finances from the Research Council of Norway in 2020, and this phase is called OceanLab. And I want just to mention that some of you have heard the concept OceanLab and FjordLab being mixed, but this shows actually the connection between the OceanLab project and the overall FjordLab concept. So OceanLab is the first phase. The next phase is the Ocean Space Center FjordLab project. So we will receive funding from the state budget to further develop what we have started in phase 1 in the OceanLab project. We are even considering a phase 3 if we see that it's necessary in order to meet the needs with regards to full-scale research in the future. FjordLab will stretch from Trondheim and down to Ålesund in the next phase. So what you see in the dark spots here is the equipment and the places we are developing now in phase 1 in the OceanLab project. It includes infrastructure in fish farms, in test area for autonomous ship, in the underwater robotics and subsea facilities, which you saw the very nice movie from, and the marine observatory. And also we are starting up the work on developing this e-infrastructure for the OceanLab, which means that we will develop an infrastructure that makes it possible to share data between all these domains. This infrastructure is extremely important for us because it will actually help us further develop our capacities in research, sharing data between the different domains. The phase 2 will also include Ålesund, as you see, where sea trials and simulation and visualization will be the main topics. This slide shows the main application areas we have focused upon in the phase 1 OceanLab project. On the left hand you see the subsea facilities, which is the autonomous underwater robotics laboratory led by Martin Ludvigsen. The second is the test area for autonomous ships. I'm the one in charge for that one. The third application area is aquaculture and fish farms. And the fourth is the marine observatory. And as you see, we have also a node. Oh, sorry. I think it's going to, no, yeah. No, it's too early in the morning for me. Okay, so the lower picture shows the e-infrastructure, and I think this slide also shows how this e-infrastructure will actually make us able to connect the domains that we are investigating in our research and testing and verification activities. And that's the same also for the control room facilities that are being built at AUR-lab. This is also something that we can use in order to combine the knowledge and data from the different domains and make us able to do research in other ways that than we have done before. I want to go more into details in a test area for autonomous ships. I think there will be others speaking about underwater robotics today, and maybe also from the marine observation and aquaculture. So I will go a bit more into details on the second node of this infrastructure, which is a test area for autonomous ships. Test area for autonomous ships was established in 2016, actually. It was started by Kongsberg Seatex in Trondheim, together with NTNU and SINTEF, the Port of Trondheim, the Maritime Directorate, and the Coastal Administration. Actually, it was Gard Ueland in Kongsberg Seatex. He went to the Netherlands and saw the living labs for autonomous vehicles and said that, why doesn't we have this kind of laboratory for the autonomous ships in Norway? We are a global industry in Norway, in the maritime industry. We are world leading, so why don't we have this kind of capacity? So we came home and asked the other of us to join, and we thought it was a very good idea because it will make it able for us to actually both do more full-scale testing and verification of the technology, but also to make it more visible for the world. This test area will also foster knowledge building, stimulate technology development. It will drive innovation. We will use it for development of rules and regulations, and that is why the authorities have joined us in this, because they can use it to actually see the technology being used, and by that learn how to regulate the technology. And also we will, of course, collaborate with other test sites and initiatives both in Norway and in other places in the world. This test area was included in the plans for the OceanLab and FjordLab development very early, and will be further developed in phase 2 in the Ocean Space Center FjordLab. What is very nice about this test area is that it's a common initiative between the industry and NTNU and SINTEF. We share infrastructure, we share the facilities, we share knowledge, and we share data. And that's very important for us in this test area. So what are we doing in Ocean Space Center FjordLab context in order to support this test area? It's simply, for us, actually, to just buy more equipment and understand what kind of instruments and sensors and surveillance equipment do we need in order to support both the research and the testing and development we need in order to develop this autonomous maritime shipping technology. The areas we need to do more within is the detection, positioning, communication, and even navigation areas. All of these areas is important to understand and to do more work in order to make autonomous shipping safe and efficient. So what we have done is in the OceanLab phase 1 project, we have both a set of sensors. These are portable sensors that we can bring into ships and the technology platforms, such as cameras and positioning systems, that we can take on board different vessels in order to run anti-collision and some collision avoidance tests and so on. We have bought 2 radar systems. One will be installed at Vanvikan, at Fosen, at the other side of the fjord, and one will be installed at Lade. These will together provide a nice coverage in the area where we are doing most of the tests today. We have both weather stations. One is already installed at the Port of Trondheim, and we will buy 2 VDS transponders. VDS is a kind of new technology based on AIS and VHF data exchange technology. And we will also buy workboats. I will show you some images. In phase 2, in the Ocean Space Center FjordLab, we will extend this list of instruments and support it with, for example, more radars, lidars, wave radars, radar platforms, and so on. I think this will be adjusted as we have learned a lot in phase 1 in what kind of equipment we need, and so we will discuss this further. Yeah, I want to show you this one because I'm extremely proud of making us trust the new technology. And that's not very easy always, because we know that technology that is immature can also have some problems. But we have decided to buy full electric workboats, and Skarsvåg at Frøya will deliver this one with technology from Evoy. But we needed to include a very small range tranquilizer in order to make it sure that we can get in from the trials at sea. But in principle, it's 100% pure electric. And we will use this one for both installation, operation and maintenance, research, and testing and verification. This is actually from a project that we have recently done for the European Space Agency. But I think this slide shows nicely what this test area for autonomous ships can be used for. There's a lot of research going on, not only on the technology side of the autonomous ships, but also on how the autonomous ship will fit into the logistic. So we can use this test area in order to test the different concepts on logistics. But of course, we also can use the test area to test communication and navigation opportunities. And we also can use the test area in order to see how the autonomous ships fits into other application areas, such as the aquaculture, subsea, autonomous maritime, and marine observatory. And we can use the autonomy in other domains. And this is because we actually are developing FjordLab such that it makes it able to test in the different domains. And I see that I have only 3 minutes left, so I will be very quick in the last slides. But I was also asked to show a few examples on the research activity we're doing in the test area. It's very hard to pick a few examples, but I have chosen some that really shows how the test area is being used. The first one actually shows the connection between the simulation modeling activities we are doing both at NTNU and SINTEF Ocean. This is something that we have done for a long time. I don't think I need to tell you about this. But you see the connection between the simulation, the laboratory activities, where we have verification of the design. Then we have also the sea trials, that is verification of the contracts. We do not have much activity on the sea trials right now, but Ålesund node will actually also build up capacity on that one. On the right hand, you see the activity we are doing in the test area for autonomous ships today, because we're testing the advanced technology and system development activities in this area. The image you see from Yara Birkeland at the fjord is unfortunately from Horten, because I couldn't find a very nice one from Trondheimsfjorden. But I added the vessels we are using in Trondheimsfjorden, which is Kongsberg Seatex Ocean Space Drone 1 and 2, and the Milliampere, which is owned by NTNU. And these are extremely important technology platforms for us in order to test, also develop and test and verify different technologies that we need to install on board Yara Birkeland in the end. Sensor fusion is an area where we are doing a lot of research activity. This is an example from a postdoc activity at the cybernetics department in NTNU, where we are using different cameras and sensors in order, and we are fusing this data in order to understand the situation around the autonomous vessel. We are doing route planning and docking. This is an example where we have used the information from the weather station at the FjordLab infrastructure in order to develop a model showing the wind profile where the Hurtigruten at the Coastal Express is docking, usually. And sometimes this wind situation at this site is extremely difficult for Hurtigruten, and they need to go to Ila, and they want to know this before they come there. And then I'm using this sensor information in order to decide where to go. Human in the loop. I don't know if Tor Hukelås is here, but Tor Hukelås is the image I get in my head when I say human in the loop. But of course, we need to also investigate this for autonomous shipping. And the control centers is a very important asset for us in order to test and verify how the humans are involved in this loop. We have run tests in order to see what kind of sensors we need to make a safe autonomous operation. Using radars, cameras, positioning systems, and everything we can get in order to see how it can be safely done. Asgeir is very eager to kick me off, but I have only one more slide, I think. And this is a very important project for us, extremely strategic important, because this is the future for digital twins in the ocean. SINTEF Digital is actually the technical coordinator for this project with the 56 international partners and very large budgets. And in this project, we will develop and launch a digital twin of the ocean, meaning that we can use this project also to build the digital twins of the OceanLab and FjordLab infrastructure and use this as a tool in our research in the future. Some takeaways. FjordLab makes the Ocean Space Center unique by closing the loop between simulation, laboratories, full-scale testing and verification. FjordLab will facilitate technology and knowledge transfer between ocean domains through making the complete infrastructure and data from it available to industry and other stakeholders. We have only seen the beginning of the use of FjordLab, and several new large research projects are being developed, and it attracts both national and international research communities and industry. Thank you.
Okay, we have time for one question, if there is any. Please, yes.
What's the difference between OceanLab and FjordLab?
Yeah, I know this is very confusing for us as well. But you could see that we are developing FjordLab in 3 phases. And the first phase is financed by the Norwegian Research Council, and then it needed to have a name, and we gave it the name OceanLab.
Okay, Beate, thank you.
Thank you.
This is a gift from NTNU.
Nice, thanks.
Yes, within the rules. The next speaker is Erik Dyrkorn. He is from Cibus and will also speak about the zero-emission autonomous urban mobility. So, you know, and I give a warning when it's 2 minutes left. Yes, you should. Okay. The stage is yours.
Is the mic on? Yes, okay, very good. Thank you. So yeah, my name is Erik Dyrkorn. Good to be back here. I used to work at Marintekniske for 10 years. I was so lucky to be among good people so that we started a company called Blue Eye Robotics in 2015. That's still operational and well, I see that's really interesting, but even more interesting, I find, is that I got an opportunity 2 years ago to be part of a founding team behind Cibus. And we make maritime autonomy for mobility changemakers, as we say, because our customers, they will change how we think about mobility on the maritime sector in many ways. We're known for this design of this ferry. It's an urban mobility concept, unmanned, and it's driven by our Autonomy platform. And I'm going to tell you a little bit more about that. But first, we're building a team of top talents, and maybe you recognize some of these people on this picture. I'm very happy to see that some of the best students that are working with the milliampere prototype that we saw a video from just before, they want to come and work for us because our technology builds on that, on the research that is done at NTNU and SINTEF on that. and we have 11, I think it is 11, now we see a picture of 12 here, part-time employees, and 18 master theses being written for Cibus at this moment. So that collaboration is just fundamentally important for this company, so we can grow with the best people in the industry that are actually being educated here with the world's first prototype of this kind. So going internationally, I think this will be one of the key areas that we will keep Cibus going. We also have a strong board of directors. You saw one of them right here. Asgeir is part of that, of course. Has a finger into anything that is interesting coming out of this institute. But also we have industry players like Tore Ulstein as an advisor and investor as well. And very also happy to have the CEO of Torghatten with us as board member, and they are investor and really active partner with us going now into the market. Now there's a question that many asks themselves. Why do we need autonomy? What is it good for? Well, it's fun, that's one thing. We can see cars drive by themselves, you can see buses drive by themselves. But you can actually get radically new business concepts out of autonomy because you get so different cost structures, both from CapEx and OpEx. Reduced crew cost is one. Some segments can be unmanned. But you also get operational efficiency from having the whole ship integrated into one sort of intelligence that can optimize the operational profile and saving fuel cost or energy cost dramatically. So that in itself could be one argument to implement some sort of autonomy on board even existing ships. Another thing is that it expedites zero-emission mobility because it's so much easier to drive autonomous ships with electric drive than with conventional technology. And that is going hand in hand, driving zero-emission mobility on water. Autonomous mobility has barriers, and we know that. Car industry was really peaking in 2017, I think, what Gartner Group called being at the peak of inflated expectations for autonomous cars and digital twins and all these things that were going around it. We're now into what is called the trough of disillusionment, where nobody knows what's going on with autonomous cars anymore, and everybody's sort of confused, where is it going? Regulatory frameworks is one of those barriers. Business drivers, who is actually making money from autonomous mobility, and how does it scale? Societal acceptance, will people accept having autonomous vehicles driving around, and how do you integrate them into society in a safe and efficient manner? These go for autonomous mobility everywhere, but there's one way we can circumvent these barriers, and that's what we're doing in Cibus. We're making simple operational domains and commercializing autonomy where it's safe, low risk, easy, and the autonomy is never really, can really hurt anyone. Like an autonomous car is like 1 second away from disaster all the time. An autonomous ferry on water, like you see here, may never be in a situation where catastrophe is close by. It's just, it's safe. And hence, we can push the barriers of regulations quicker, and hence scale our technology based on this sort of operational concept, and then make autonomy commercially viable, and then eventually scale into different industries as well, or segments. Another way is the retrofit of existing ferries, still being manned and still being everything inside the regulatory framework, but saving cost on crew and energy. And hence, maturing autonomy and regulations, let's say, from the outside. We built the world's first autonomous ferry. I'm saying we, Cibus didn't, NTNU did, but we hired the people that did, all of them, more or less. So, and we're hiring also all the people that are still working on that at NTNU, and they come and work for us. So that's part of the ecosystem that we're sort of building here together with NTNU. It's a super important collaboration, as I said. And we also, we work closely with DNV regarding classification of of these type of ships. Actually, the DNV department for making regulatory frameworks on autonomous ships. Much of that is sitting here in Trondheim, and we actually hired some of the best people in there, and the CTO is sitting right there. You know, we took him and said, we need that expertise, and we can sit on both sides of the table in a way to build this framework together. And they use milliampere, NTNU, and CBus as part of the process towards becoming a world leader in say, certifying autonomous ships. Really interesting position to be in as a company. In addition to autonomy, we're building also, let's say, even more important maybe for the company is to build a complete simulator suite, end-to-end simulator, where the full autonomy platform, including the control system, the physics of the boat, and geography and everything is put into one setup, and then added to make it visually nice, open data that is from Google Earth, which is kind of interesting that all this is for free. Oh, more or less. We pay with data, I guess, or all these things. But so that is what will make the autonomy platform scalable. Because through the autonomy, we can verify our algorithms, we can test what we're, everything we're working on, and we can train our autonomy for almost any situation, for new customers, new segments, and new locations very quickly, and just run that through the simulator before we actually execute in real life. And then limit the time you need for verification before you can actually put it into a commercial operation. So we believe this is where we will work the most going forward. So the business model, if you will, on one level is we have the autonomy platform, we go through the simulator, and we have the CBus autonomy service, which is actually the product or the outcome of the company. And this is what we deliver to customers, the change makers. First in the urban mobility segment, later in different segments. CBus has a unique combination of autonomy, prototypes, and simulators that gives us a head start in bringing autonomy to the market. That is a position that stands really firm today, and we get inquiries from companies and research institutes all over the world that want to collaborate with us. But as I say, this is not true unless we actually start commercializing this in real life and start making this into a business. That's when we are world's best. So let's make that happen. There are different segments that are, let's say, on the list over what is best for autonomy, urban mobility, car ferries, very simple operations, inland waterways, another one that is sort of going in a very confined or easily defined area. But what is more interesting, I guess, is the new concepts that will emerge from autonomy. That gives radically new business ideas and can actually drive how we move things around in a radically different way. So, part of the concept here is to run this in the network and then start by putting people on shore, overviewing the network, and that being step one for unmanned mobility. We believe that will actually be the first really unmanned, commercially viable urban mobility solution in the world. Yeah, I think I'm going to just fade out and not go through everything to make, he's my boss, he's on my board, so I need to make him happy. But just one word, multimodal micromobility. That's part of what, we're very part of. It's just a fun word. Anyway, the world is our playground. I think this is where we go later. Thank you.
We have time for one question. Any to CBus? Yes, please.
Can you comment a little bit more about regulations? Where are you and what do you think needs to be changed?
It's the big question. It depends on who you talk to. Different countries have their own regulations, and that's one reason why we go inland waterways, is that the national regulations that sort of regulate that, rather than open seas, that, you know, IMO, it's a very big, slow-moving body. So Norway has its process to make this happen together with these research communities here, and the test area for autonomous ships that is also here. So that's it moves in that direction, but also other countries are more aggressive than Norway. So we're looking at that as well. I was in Dubai last week. They want to make this happen. I think it's important for us to collaborate with those national regulatory bodies that want to make this happen first, but safely, underline safely.
Yeah. Erik, yes. This is a gift. It could be gold-plated because you kept the time.
Oh.
Anyway.
Thank you. Yeah. Good deal. All right.
Yeah. The next speaker is Kjetil Skaugseth. Kjetil, he will speak about subsea robotics, offshore game changer. Kjetil, he is employed at Equinor, but he is also a colleague here at NTNU, and a true example of how well NTNU and our department is collaborating with the industry. So he's adjunct professor also at NTNU, and heavily involved in 2 centers. One of them is AMOS, the other one is KAROS. Everything ends on OS. How come? Kjetil, the stage is yours.
Thank you very much. Thank you very much for inviting me, having me. It's really good to see all of you, and also thank you for giving me this topic. It's very easy. I can say subsea robotics and offshore game changer, yes, and we're done, right? But okay, so let me bring you a little bit more context to that. I'm sure you're familiar with, I won't go into details on the different robotic, but I'm sure you know about the loom. But we have incorporated a phrase called underwater intervention drones, UIDs. And why do we do that? It's because we see, it's not like we need only one type of underwater AUV or ROV or underwater intervention drone, but we need a variety of them. And we also need for them to work together. We need for them to be able to have an interoperability, both with us as an operator and potentially also other operators, so that there's there's a greater potential for the industry. So I'll give you a couple of examples of that. So this is just a picture showing some of the what we call underwater intervention drones. But of course, this is super cool and exciting. But of course, that's not why we do it. It's business. And you heard Tone yesterday talking about the Equinor strategy. And if there are 3 phrases I want you to remember from that, it's what's in the center here. It's always safe, high value, and low carbon. That's how we measure every activity in our company. And to relate that back to subsea robotics and the underwater intervention drone, the always safe has to do with reducing the human exposure offshore. And also then to improve our understanding of the technical integrity, or to do that in an even more inexpensive way. But also to reduce response time. Because if there is an indication of something, and we need to call and get a ship with an ROV, it takes a lot of time, right? So what we want here is to have resident subsea robots to be able to respond in an even more swift manner. So residency is a key. When it comes to the high value, it has to do with reducing the operating cost, of course, and the production efficiency, but also to enable new ways of working altogether. And I come more back into that. And when it comes to low carbon, it's of course about reducing the CO2 emissions from supporting ships, but also to improve our renewable business. Offshore wind, for instance, I also come more back into that. So this is aligned, and also it's an enabler for remotely operated factory for new field developments. But if you go take one step back and see what we have presently, these are our subsea wells in operation today, and as you can see, the ship that we have to call, it's probably the most expensive tool that we can pull out of the toolbox. But if we instead have then subsea robots at our fingertips that we can deploy swiftly, it's cost efficient and it's rapid. And this is the subsea wells. But if we look at the offshore installations, we have so many, and they are of course also aging. So we need to inspect it in a cost-efficient way. And the picture to the right is the grid of the pipelines that we have on the Norwegian continental shelf. And of course that needs inspection as well. And not only the existing infrastructure, but looking into the project portfolio that we're having, these are some of the new projects in our portfolio, and we have a record high activity level, really, when it comes to here you see FPSOs around the world. But what is perhaps also most interesting is to see the biggest project that we have. Even though those projects are really big, the biggest project we have in Equinor is the offshore wind project. And offshore wind also needs, of course, in subsea inspection in that sense. So an inspection on offshore wind is not only in air, as you can see here, but it's definitely also subsea. And to give you a sense of context on the scale of things, I added this picture. And this is just an illustration, but still it gives you an idea of the dimensions. On the right-hand side, you have Aasta Hansteen, the spar FPSO. Hey, what happened there? The spar FPSO and the Vøring Plateau, and to the left you have Hywind Tampen. And what you're seeing is that dimensions are quite immense also on the offshore wind side. The one in the middle is a smaller, unmanned production platform, and that also tells a story, because if we're going from the right to the middle one, it's obvious that will reduce cost a lot. But what is an enabler in that sense is to have autonomy and to have remote control and to control from shore. And in order to do that, there is a suite of tools that is needed, and subsea robotics is one of them. And the middle one, it could look something like this. And so this is remote to control from shore, and with extensive use of robotics. Okay, so what is important for us is interoperability. So as I said, there is not one size doesn't fit all. I mean, they have the different subsea robots have their own unique capabilities, and instead of over-speccing those, it's a matter of harnessing the value in each in a good way, and also then to be able to standardize and to scale this. And one key element to that is the subsea docking station, and that you can see on the left there. And the key there is also then the standard interfaces that we have, so that everybody understands how they can connect to us, because that is really reducing the threshold for suppliers to become a supplier to us, and also small startup companies that is then able to understand, okay, what does it take for us to become a supplier to Equinor, for instance? Well, hey, you need to be able to communicate with this one. If you do, you're good to go, if you're qualified. So the point is, no matter how you look like, if you're able to connect there, you're good. And then the question is, okay, but how do you test that? Well, what we have done is that you heard earlier today on the test center in the Trondheimsfjord. This one is located in the Trondheimsfjord. So you're actually in your backyard. You're able to test this. And when I say architectural control in this figure, it's a matter of, we as an operator, we need to take that architectural control and make it such that all the suppliers are able to deliver in the same way, in order to have a healthy competition also. And also for new companies, potentially the best ideas that you have are able then to penetrate into the market. It's like the chocolate commercial. The best chocolate is not made yet, right? We're working on it, and it's the same thing here. The best subsea drone is not made yet. It's it's a constant evolvement, and it's important for you to understand that it's not the winner takes it all. It's a variety. Okay, so the subsea docking station, and you heard about the test center in the Trondheim fjord, and there's a picture there of the rector of NTNU opening that together with Anders Opedal. And it's located outside the Trondheim Biological Station. And we're using it. This is this is Anna, the new rector, with Martin and also the Anders and AUR lab, where we are testing subsea drones for Johan Sverdrup. So and we have been there a number of times, and this is important for students. It's important for the for the master students. It's important for the PhD students, and the research community as such, that you have this facility in your backyard, and you can utilize it. Utilize it for research, education, and for industrial qualification, and to verify it. And I mentioned Johan Sverdrup because now what we see in Equinor is that we are rolling this out in a wide manner. And these are some of the fields that we are considering the use of underwater drones. Some of these are already signed up. I mean, Njord is already decided upon and was signed a contract in 2019. Johan Sverdrup, as I said, had an invitation for tender, and several suppliers were testing here in Trondheim. And the list goes on and on. And this, we see this as a natural part of the field developments going forward. So this is happening. This is not far into the future. This is happening right now. And of course, we have used subsea drones for many years already, but this is a matter of increasing also the level of autonomy and remote control. But if we want to step into the future a bit more, we're also working on that together with NTNU. And we call that cooperation of heterogeneous sensor platforms, or game of drones, as we also call it. And the point with that is not only to have, a subsea drone or, doing this thing, but it's a matter of having different drones cooperating. And it's not the swarm, but they are distinctly different, and then still cooperating. And looking at the observational pyramid, I mean, how you can relay information and help each other also in this vertical dimension. So the subsea is a part of that. And I don't have time to go into the details of all the benefits, but why cooperate? It's a matter of really enhance the capabilities. But if you want to do that, of course, there are some important enablers in that context. And again, this is, even though we are looking into the future, still we are in the process of doing this. In 2019, we did this test on pipeline inspection, which is a simple example of a drone helping a drone. In this case, a Hugin being assisted by an unmanned surface vessel. So looking something like this on board there, and then you can widen your area of response to the mission at hand. So to round off, and because I see Asgeir is getting an easy, I just wanted to highlight, you mentioned the CAROS and the AMOS. Yes, sure. And so this is important collaboration arenas, and I only mentioned a few of the research collaboration arenas in which we are really deeply into interaction with NTNU and with others on the use of subsea drones. And also we are hiring. I mean, there is an opening in the Karos for a PhD, for an eager PhD student, and also Equinor is hiring at present. So I think that is, if you want to be a part of this, both as inside either of this, but also as a supplier, to understand that you have all the tools that you need just outside your door. It's amazing. So to answer the question, is it an offshore game changer, subsea robotics? The correct answer is yes. So with that, I say thank you for your attention.
Thank you, Kjetil. We have time for one question. Any to Kjetil? Clear as water. Yes, please.
What is the biggest actual operational benefit that comes from these drones, you know, in terms of what they can do? I'm thinking outside of inspection, traditional like inspection and just checking status. And do you foresee that they actually do?
Yeah, I mean, we have you have a roadmap or a sea map, I guess, of how we are evolving. You know, taking it from pure visual inspection and to more heavy actions. But of course, just the information. If you have an indication of, say, a leak, for instance, a leak detection, and to be able to deploy an underwater intervention drone to actually fact-check that. Is the indication correct or is it not? Because there are big decisions that are being made and that are time critical as well. And to have that tool at your fingertips, rather than to having to call, you know, in a ship and all that, it's a tremendous improvement. So in a way, you might say that, you know, you have the planned inspection and all that, which is kind of a long, you know, it can be planned ahead of time, but you also have the operational things, that the information that you need as an operator if you're in a control room of a field. So you have both.
Kjetil, this could be gold-plated as well.
Thank you.
Thank you. I'm supposed to be the next presenter, so if you wonder why I were keeping the time so strict, so no. No, it's actually, frankly, not only that. I will come back on that after lunch, but all right. I'm going to say something about AMOS. It has already been mentioned, and I must also say that it started not only with AMOS. This started with CESOS, where actually, so I were lucky to be trained in how to run a center of excellence. And the previous director, he's sitting just there, and a lot of other key persons. Odd is also here. So in a way, we were born into this center of excellence type of training. But it's about systematically work on fundamental research. And we at NTNU and our department has been so lucky that we have been having close friends. We have SINTEF, we have DNV, and Equinor. Unfortunately, in the next round of Center of Excellence, this type of industry collaboration is actually not allowed anymore. And I think that is actually a wrong direction. But anyway, just also to mention, both Torgeir and Odd is of course also deeply involved in AMOS. We have 3 projects in AMOS. One is on technology for mapping and monitoring of the oceans. The other one is on marine robotic platforms. And the third is risk management and maximized operability of ships and ocean structures. And in a way, I think the amount of efforts is similar for all these 3 projects. And but where we maybe have made most new results is on technology for mapping and monitoring of the oceans. So we have really started to pay attention also to the ocean as such. One thing is about ocean health. The other thing is also how ocean could be an important resource and already we know that for fisheries, it is also for aquaculture, but there is also, we are looking into new trophical or lower trophical species. It could be plankton, etc. So today I will speak about that, but we could have had probably a much longer story also on the third project, just to say that. But what is AMOS? And what is the main deliverable from AMOS? That is people. And I must say that the older I'm getting, the more, and I will say that I understand the importance of people. It's the graduated, masters, PhDs, postdoc, because it's by all of you we are scaling up. And one thing is what we do here, but this is also knowledge that you are bringing out, and you become change agents wherever you go. And I see it is really working. So we have about 700 or more than 700 graduated masters, which is associated to this. And there are more than 200 PhDs, whereof 121 has already graduated. And but we are basically measured not on that. We are measured on our ability to produce high quality papers with high impact. So that is the way we are measuring that. Is by in terms of journal papers, books, keynotes, and there are also hundreds of these, or thousands now, more 1,800 scientific papers. So we can actually make books of this. But I will also say that where does AMOS start and where does it end? I don't know, frankly. So we have a core budget inside AMOS, but this is also, as it was for CESOS, it becomes an engine where we are creating numbers of associated projects and activities. So today, I think most of the people here from NTNU is involved in AMOS in some way or not. I must also say that this is nothing we do alone. Because if you are working with Center of Excellence, you are not, I'm probably a little bit more starting to be known for this. Because we are playing in Champions League every year. And not only that, we are also in the final every year. So we do this together with international collaborators as well, and our partners. So in a way, we are not, I will not say that why is marine, why is this offshore is so important for Norway. Well, we are in a way mirroring the industry, and where Norway is actually a big player, and that is numbers of companies as well. We are also part of a supercluster, and if you're looking to AMOS, we are almost everywhere here. So and one of you could say the learnings we have is to focus on the fundamentals, and then use it in one area, and then take it from that to another one. If you take, for instance, when Torgeir started the offshore wind, and you heard yesterday, that started in sometimes 2008, 7, 8. And Torgeir, he decided just to put tremendous efforts in order to educate, graduate people on that. And in a way, he saw that this need is coming, and we see now, some years after, that they are in a way creating new industry of big importance. We did the same when it comes to autonomy. Already in 2010, we saw that this will be a new shift, a new change, where intelligence will increase, and we will also see the era of robotics. So that is another way where we are actually pushing the throttle to make a change. If you take aquaculture, Odd, I don't know if he will talk about that later on. He did a similar thing, how to prepare, you could say, knowledge, competence to take that role. So we are doing that, and we have colleagues on biology and also from cybernetics, and everybody here may have heard about the snake robots created by Kristin. Fabulous. And now Tor Arne, he decided that we should go to space, And we are going, and on the 13th of January, we launched the first small satellites. And this is also headed by a new colleague here, Eirik, which is having birthday. Happy birthday, Eirik. Just to mention that. But I think that is crucial to see these trends. And what is a new trend, really not new, but rediscovered, is sustainability. And it is no doubt that sustainability has moved from talk, PowerPoints, to become a part of Excel sheet. And when I'm saying Excel sheet, you can wonder, what does that mean? It means it is on the bottom line for the companies. It means that the CEOs are looking into this. Owners are looking into that. And you saw that yesterday when Bo Serup Simonsen were speaking about zero carbon shipping. The chairman of that board is Sørensen. He is actually also the chairman of Maersk. So this matters. And when we are speaking about sustainability, it is economic, it is about environment, but also social. And I must say, a learning for me has also been is about to be aware about the ecosystems. And COVID has also learned us that if we they could actually harm us dramatically. So when we are going to spend, and we are spending more than 1.5 billion something in here, that is kroner, but that doesn't really matter. But it's more important, where are we putting this, I would say, the intellectual capital of people? Where are they spending their resources? And doing that, we are looking into global challenges. We have to enabling technologies and the license to operate and to see the holistic picture. And believe it or not, if you may think that, okay, I'm working in a center of excellence, that I'm deeply in just one corner. That is not the future. The future is interdisciplinary. Collaboration, being able to mix that. That happened already also in CESUS, and actually more or less marine cybernetics as a field was born in CESUS. So, but we also see a shift here. It is technology becomes accessible for everybody. So that has also been a dream, and where we have been chasing. How could we create technology that make it possible for students, for also society to go into the oceans? And one reason is that, for motivating me, is that we should care. And when people start to care, they will start to challenge their surroundings, industries, politics, and in order to make a better life. So we have actually seen now the explosion in this robotics everywhere. And when we started the AMOS, these were actually supposed to be hairy targets when we started AMOS. It was phrased, approved by the board, and we said that we should ramp up the third one, the mapping and monitoring coverage 10 times at the cost of 110. But what we have seen, not only because of AMOS, but in the industry around us, we are now ramping up maybe 1,000 times. And of course, it's coming a lot of new challenges out of that. So we have seen a shift in technology. But what you see here is a picture of the technology platforms we have at NTNU in collaborations with SINTEF, University in Tromsø, Equinor, and where you see we are actually working underwater, on the sea surface, in the air, and also in the space. This is already told about by where we are. We also see the secret of success, I would say, in Trondheim is actually the collaboration we have, in particular between NTNU and SINTEF. We are married, and then together with big partners like Equinor, DNV, Kongsberg, we are in a way winning. So this was a game changer. And this is also an idea that was born between Equinor and NTNU. How could we actually put the robot subsea? And I must say I was extremely proud when we launched this. But we also have another program, and that is on drones. and in the air. So together with NIVA, we also have a national infrastructure where we are now building up this type of capability. But this, I think, can maybe stop my presentation in order to keep the time.
Nine, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition and liftoff.
We actually decided to go to space, and you saw the information pyramid, and I think that is maybe some of the most important thing with a center of excellence. We can set some targets, and then we just execute. And I must say now we are trying to set up again national program where we are going to take position there in partnership with of course SINTEF and many others, such like FFI and Eirik. He has that as his main thing to fix it. You will have colleagues helping you, Eirik. But by that, I think we should, I will say thank you, and it's time for coffee. So I will also chair this session. So the first speaker is Martin Søreide. He is working in scale, but also a demonstrating example of how you are shifting from one segment of the blue economy into another one. As far as I know, you were also working in Equinor. So, and this talk will be on offshore aquaculture. So please, Martin.
So thank you for inviting me, as everyone is saying. It's kind of special to be here 20 years after finishing the education. So it's nice to see all the good professors I had here, colleagues from studying here, fellow students. 20 years ago, a bit less here, but the main focus is maths and physics to include that in aquaculture. So my background is from Marintech, doing structures, hydrodynamics, and everything. Then I went to Equinor to work there for 12 years together with Kjetil, Tone, others. But then I changed to aquaculture, to fish farming, which is kind of special when the oil was going up and fish farming was quite stable. But the impression after 8 years is massive. So using the competence in such a business is just as fun every day. So that's the main thing. This is the one, Asgeir? Yeah. No, that's the one. Yeah. So what's the most exciting thing? To be to produce oil with the APL boys at Heidrun, or to kind of look at aquaculture or fish farming? This is a site outside Bjugn, a huge site. This cage is 200 meters circumference, so it's quite huge. So this is cages produced by plastic, but there is still on our cages about 30 tons of steel to make strength and so on. The most exposed cages that I have designed and in operation now for 3 or 4 years is about HS 6.5 to 7. And the main thing then is to understand the purpose of the cage, which is to house the fish. You don't walk on Heidrun neither in HS 14. You don't walk on these cages in HS 3. But you have to make the fish safe in the cage, which is the main principle. So in this cage, it was about 200,000 fish, quite enormous, quite exciting to see all the fish, the food production, and every year in our cages and nets we produce about 1.5 million ton salmon every year worldwide, from Tasmania to Campbell River in Canada, Vancouver Island. So it's very exciting. If there are any students here, I need some students for summer jobs this summer, which should be interesting on mooring of barges and so on. We hire, in my department, I have now 15 engineers from Marintekniske, and we hire more. We still need people. So scale is a collaboration actually of several companies. So I worked in a company called Aqualine since 2014, where we produce cages, nets, moorings, and everything. This is a total overview of the products that we have. Now we also have Moen Marine producing boats. We have Steinsvik on the barges, cameras, and everything, and also Aqua Optima on the land-based. So we have a lot of products, but we still need more, and we still need the snake to do inspection of our cages, the nets, and everything. So there are enormous opportunities in the aquaculture business. We also need maybe vessels from Seabus to bring people out and to bring salmon in a sustainable way to the factories again. So it's up to us. We have a total revenue of about 2.7 billion NOK now. When I started in Aqualine, we had a revenue of about 300 mils NOK. So it's increasing rapidly. 40 years of experience, and now we have about 800 employees all over the world. So it's really exciting to be there. So then, back to the exposed aquaculture. The title on this one was actually offshore aquaculture. I changed it to exposed because offshore is quite different. Out on Heidrun, Asgeir, and so on in HS 16 meters. Our structures, which is the flexible pens, we are now, as I said, going with these ones up to HS6, HS7, which is quite amazing. And we do that by research, by development, up at Marintekniske in the model basin, calculations, and also using the competence hub that we have here, which is one of the most important things. So doing thesis and so on is important. So the challenges in aquaculture is access to new areas, sea lice, I come back to that, mortality losses, documentation and control of pens and cages and so on. And also to combine open aquaculture together with closed aquaculture, which is now really important for the business. And our focus going forward now is to do kind of everything. We want to do closed aquaculture, we want to continue with open aquaculture, so open pens and so on. And we want to do semi-closed, which we have done. And we want to do Subsea together with Frode and his competence hub. He's going to talk later. So these are all activities that we are working on. We are also working on offshore to assist on the installation with net designs and so on. So it's a wide spectrum of opportunities, but you have the main focus always is the fish. So you have to work with biology, and the main difference on moving from oil and gas business to aquaculture is to understand the kind of aspects working on design. Because if you take an offshore platform and design the accidental limit states, Torgeir, you can actually control kind of the risks by shutting down the production. But you can never shut down the salmon or the biology production in a cage, which makes the consequence slightly different. So that is a main focus, and I also talk a lot to the directorate about this, because you have to understand the consequence and not only the probability and the total risk assessment. Exposed aquaculture, moving to higher waves, higher currents, and so on. You have to focus on biology. You need constructions like this to handle all the environmental loads and so on. Then it's the risks and reliability, which is kind of in the start for the aquaculture business. But you have to work on risk analysis and to understand what can happen in these constructions and sites. Of course, operations. There are a lot of operations at the sites on handling dead fish, putting fish in and out of the cage and so on. And we are now working on making all these operations automatic. To bring the fish in automatic, to take it out, to take all the dead fish out automatic, and so on. That should be, or will be, the focus for the next 5 to 10 years. And we believe that this should be called kind of precision aquaculture. You need methods to control this, and you need systems to help you control this. Both from areas, to control areas, as we talked about, Asgeir, and also the fish and the biology, because the fish is always, that's what's bringing the money. So it's always the focus for a fish farmer. And if you go 20 years back now on fish farming, it was completely different. It was hard making money and so on, but now it's moving upwards. And then it's also a big opportunity to use competencies which is present here. And so until now, it's a lot of the operations and so on have been done manually. It's based on experience. You see a dead fish and you take out 2 dead fishes. You see an ill fish and you do things to control the matters and so on. But we want everything to be automated, predictive, and have system to help us with kind of decision support. And we have about 30 people in our company working on this now, together with NTNU and so on, SINTEF, to make systems and so on to control this. Then this is kind of so fun, because research development, working with the model basin up here, which is now being refreshed and so on, it's so interesting. And the most interesting part then is to bring everything of this into aquaculture. So why do we test our cages up at Marintek? We were the first ones in aquaculture to do that. Why do we do it? We have to verify our models. We have to check our softwares. We have to bring this information to the fish farmers. When the fish farmers in Canada see our testing at Marintek, the sales afterwards is quite easy, because then they believe in our designs and so on. And the guy to the left here is one of the pioneers in aquaculture, standing beside me. He's an owner of a company and working with maths and physics with a practical guy who knows fish farming. It's the kind of a crucial thing. You always have to bring the fish farmer into design or technology. And then going together up at Marintek is so fun and so interesting, also partly because people at Marintek is fantastic. This is a new system that we are designing now and requiring some input from Frode. That's a subsea system. We want to get beneath the lice, and we want to get beneath the main kind of wave loads, which is the main thing. This is going to be out at sea this autumn for us. We were the first ones looking at this, or one of the first ones looking at this, when we applied for development licenses. But now we are bringing this into sea, which is very interesting. This is just a video showing the tests that we did in 2016 at Marintek, checking the system. We didn't get the licenses, but now we are putting this into sea, and we need systems checking the net. We need system feeding, water feeding. We need systems bringing the dead fish out, and so on. It's a lot of challenges. We are bringing a lot of students now for thesis, and it's really, really interesting, and this will be shortly on sea. 4 more minutes, Asgeir? Yeah. These were the latest tests that we did last summer. Then we also brought a barge into the basin, a feed barge. And for people here doing the models, softwares, and so on, checking the motions of the barge and moorings and so on, it's quite easy. But the effect on doing this at Marintek and bringing all the videos and all the kind of results and so on to all the fish farmers, directorate, authorities in Canada and so on is also very important, in addition to checking the softwares and models. It's also a good picture here of the cage being built with 3D printed steel brackets, PE pipes and so on. This one is 200 meters circumference, a total volume for the fish of about 70,000 cubics. enormous. Then our focus, main focus then, is to keep a big volume for the fish. And if you look at, this is HS7. So we don't run like 10,000 seats or something that Equinor do. We can't afford that. But we check, this one is HS7, and look at the volume of the cage. And then the focus is bring a big volume for the fish, make it sustainable, and check kind of risk matters like ropes and everything. I don't want any ropes to go slack, because then I can have chafing, components touching each other and so on. That's the focus. And looking at the forces, the motions and everything. And for those of you having good glasses or good eyes, you can also see that there is a new dead fish system beneath the cage, which is kind of a same system that you use for offshore offloading. So we want to bring all the dead fish systems out of the cage, all the systems, all components out of the cage to reduce the risks for chafing and finally escapes. Because escapes is one of the most important risk matters in aquaculture. This test is being applied for design, for showing people everywhere, for adjusting models, softwares, and so on. And really interesting, and so interesting that we're also spending more time at Marintek after the summer. It's costly for us, but the effect on that is quite enormous. This, I just want to end with this one, because this is also interesting. This is a new cage that we have developed, a semi-closed cage, where you actually bring, with thrusters, you rotate the water, and then you bring fresh water up in the center of the cage, and then out on the edges on the cage, and out again, as we see on the arrows here. This will reduce the impact on the lice on the fish, but will also train the fish, and it will also bring fresh water with respect to biology, and kind of meet the requirements in the industry right now. This is actually a flexible design based on the Aquatras concept. Alfredar is probably here, no? So also a fellow students, student from us, developing the Aquatras concept. This is a flexible design of that one. Really interesting. It's been out in sea, producing fish. No lice on this one, Frode. So the industry should be aware. This is just some picture from the installation. These thrusters are huge, still automatic and so on, adjusting the speed and creating the best kind of environment for the fish, which is the main focus. And that's also for exposed aquaculture. Always think about the fish. That's the main focus. Okay, thank you.
Thank you, Martin, and you just showed or underlined my point of scaling up with people working in scale, also.
That's scaling up. That's the principle.
But definitely also that because we have had the pleasure to follow the way aquaculture has really becoming something from smaller type of business to really become professional, and your story is actually a good demonstrator of that. Do we have any questions from the audience? Yes, please.
Yeah. Okay, that's the original one is made by, it's a stiff one made by steel. So we brought that design as a collaboration with the Aquatras company to make it partly more cost efficient, to bring it into our cages as a flexible cage. So this one is made by PE pipes, steel brackets, and so on. Then it's the skirt is huge. It's like the half of the Lerkendal football field. So it's huge. It's enormous forces and everything. But by tuning it with the sinky tube, the pre-tension, and so on, we make it very stiff in water. So this one is certified up to HS2, 2 meters, not more than that. Yeah. So, and that's just to finish that, Asgeir. That's I have to say that because These cages, those are flexible. PE pipes, steel brackets, they move with the waves and everything. And that's the strength about these cages. We now see the new concepts with the big platforms and so coming. But these cages can be, they are really strong. They are flexible, living with the waves and everything. And that's the strength about them. We will see these cages being now developed even further and for more and more and more exposed sites, because they are doing what they have to do to make a safe home for the fish. Integrity of the net is the most important part, to not have escapes and so on.
When you say flexible, it's like these closed cages.
Yeah.
But this one is not closed.
No, it's semi-closed. So you still have a net part, as you see on the picture on the bottom. Yeah. And most of the closed cages are also semi-closed, because they bring water in.
The surrounding is closed. This wall around.
Yeah. Yeah.
All right. The way you describe the flexibility, it sounds like Chinese wisdom to bend, to be like a grass.
To follow
Isn't that correct, Sen? Yeah, there is something there. Okay, Martin.
Yeah. Thank you.
Thank you so much.
Thank you.
The next speaker is Frode Oppedal. And we heard about that this is about fish and fish welfare. And I'm very glad you are from the Maritime Research Institute.
Institute of Marine Research, yeah.
Sorry.
Yes. So this flexibility, could you actually make the water go over the edge instead of down again? Just an idea. Okay. Fish welfare, biology, technology based on biological principles. That's what I'm going to give some input on. So quickly, I will talk about salmon behavior and physiology, how water velocity thresholds were found or what they are, what's the impact of waves on the fish, technology like skirt, snorkel, what impact do they have, submergence, and how big can we make the cages? So, salmon, they school around and around and around. Just like if we were skating and there was a lot of us, we had to go around and around and around, not to hit anybody or hit the walls. So that's been modeled. So this first, is it not showing? Oh, oops. Oh, I can't use this. Sorry. Yeah. So this one is showing the schooling behavior. The water velocity is slack, and they're schooling. If the water is warmest on top, the fish will concentrate on the top because they like the warmest water, up to 16 degrees. If it's colder, no, if it's warmer than that, they will swim down. So in a fjord where you have a gradient, they will swim high up when it's warmest high up, and deep down in winter when it's warmest deep down. So they will not utilize necessarily the whole cage. So if you have gradients, you need a much bigger cage or a deeper cage compared to if you don't have. If you increase the water current, some fish will stand on the current instead of swimming around and around. That will happen at about 1 fish length per second. Above 1 fish length per second, then they will stand on the current. If you increase it even more, all the fish will stand on the current. If you increase even further, some of the fish will be fatigued, like you running up a hill, and they will end back here and die. Physiology-wise, cortisol levels will go up. 3 hours after, it will start going down, and the day after, it's back to basic levels. As with ourselves, if we run until we are fatigued, we will continue to create lactic acid, melkesyre, for the next hours, and it's painful. So the fish do that as well, and it won't disappear until the day after. For the fish, they will also have problems with regulating the salt. So they are in salt water, and they are less salt, so when they have to breathe a lot, they will take up salt, and it takes a while to recover from that imbalance. So it takes more than a day to recover from that. That means that if they are fatigued, you shouldn't stress them a lot straight after that. You have to give them time enough to recover. So what is the actual swim capacity? This we have measured by using a treadmill for fish. There's of course water, and we increase it in steps, and we find when they are fatigued. So that's called UCRIT, critical swimming speed. And here it's given in body lengths per second. So you see that a small fish has a relatively higher critical swim speed than a larger fish. But a larger fish swims faster in absolute units. There may also be effects of different generations, so meaning that you can select to selective breeding. Maybe they can swim faster. So here is shown that all the blue points is 2019-2020 generations, of which has been selected compared to the fish that were tested 4 years earlier. Temperature. These are vekselvarmedyr, term or poikiloterm, is it not in English? So these can swim fastest at their optimal temperatures and much slower, 20-25% slower at low temperatures. So having fish up in the Barents Sea in a lot of high current conditions is not very good compared to having them in warmer areas. And too warm Tasmania, they will die. Here, 23 degrees, the fish starts dying after a week. Fish might have parasites, and then the UCRIT itself will go down. So about 25% lower UCRIT. So this parasite was amoebic gill disease, so that's an amoeba that clogs the gills. When you're out there, you might not be able to feed every day because there's too many waves and so on. So maybe you can't bring food out there, so they might be fasted for some days, weeks, but that does not seem to affect their performance in terms of UCRIT. So UCRIT is kind of an exact threshold, but how much of UCRIT can they swim at for longer periods? So this one is showing that if you go to 80% of UCRIT, they will swim for at least 72 hours. So here, 2.5 days, they will only at 85%, they will not be able to swim more than 2.5 days. So of course, if you give them 100%, meaning the UCRIT, they will only last for minutes. But the flow the fish experience depend on the technology. Here is some examples. And the flow they experience, also the waves, will depend on the biomass, how much fish is there, what's the size of the fish. There'll be peloton effect, so meaning that like a bicyclist in a race, they will be behind each other, and they will then save energy by being behind the others. The net wall will stop some of the flow. If it's a lot of fouling, that will dampen the velocity even more. And you can find some kind of designs to dampen the water current if need be, I'm sure. At least you can draw how to make cage designs to do that. Waves. What are waves? You probably know it more better than me, but here's an example from Plateau, which is one of the offshore sites. They might start producing fish, or they want to start producing fish. So the HOS here is kind of up to 10 meters, but mainly below 5 meters. So the colors here in the middle is frequency of these waves. So they will be more or less less than 5 meters high, HOS, and the wave period is like 10 to 15 seconds, meaning that they are 150 meters long, something like that. Maybe it's slightly less, but no, yeah, something there. What is the wave action? It's a movement. If you have a particle there, if you're a fish, you'll be moved around and around. If you have very sheltered areas, like at the Faroes, where they are much more exposed than we are, this movement goes almost to the bottom of the cage, because they only have 20 meters, 25 meters. Intermediate depth, there's an attenuation of this movement, and at Vøringsplateauet, this attenuation means that all the movement is gone at half of the wavelength. So if you have a 120 meter long wave, there's no movement at 60 meters depth. So we could just submerge them, or the fish could swim down. But what do we know about this? What do we know? Do they do that? No, we don't have much data. And also, your point about movement. So your cage is moving, and the net is moving, while this yellow one here has the floaters down there, so it's sitting still. So what we have seen is that there is collisions between fish if they're in this zone, and there is collisions with the fish and the net. So of course, if the net is moving, there might be more collisions than if it's not moving. Or is it the opposite? We don't know. We haven't studied it, because we haven't been out there yet. We've seen that fish can lose behavioral control. Schooling patterns that I said can break up. Do the salmon just swim deeper and avoid this turbulent area? Yes and no. Of course, at the Faroes, it won't help because the movement is there anyway. And if there is a current also reducing the volume, there's no volume to go down into. But if you make these cages big enough, the fish will probably go down. We've indications that they do. These two papers here by Åsa from the Faroes. But we haven't studied it enough. If at the same time it's warmer deeper down, they probably go down. But if it's warmer at top, and you're also feeding at the top, then they might not go as much down. And then there's the day and night differences. We need to study it more. Fish can become seasick. Well, seasick. We haven't proved seasickness, but they get stressed if they are transported in a wellboat where there is a lot of wave action. Feeding, will they reduce their appetite? Can they find the pellets in all these movements? We don't know yet. Another few principles of designs. So you've got the normal cage, yeah. You've got skirts. So that's to avoid the lice larvae coming into the cages. So to get less lice. The snorkel cage is a bit of the same, but they've reduced the area where they skirt. And then the fish is still able to go up and down. And then you got the submerged sea cage. Martin was lacking something, so I'll come back to that. But the fish, yeah. And then you can put things inside to make the fish voluntarily go down, such as feed deeper. You can put lights and attract the fish to go deeper. And then you got the semi-closed ones. If you use skirt or snorkel, you are stopping the water flow. Of course, there's much forces working on your cage. And the water, yeah, and by not stopping the water flow, you will get reduced oxygens. So this is just reference controls, reference of meaning that we measure the oxygen level outside cages, in control cages where the flow goes freely through, and then we measured it in skirt cages, and you see here that it's much more red and yellow, and that means that there's much lower oxygen levels there. Of course, you can start making a water exchange, but yeah, you have to beware and do something about it. How often do a salmon jump or roll at the surface? And why do they do it? Do they do it because they are feeding on insects or whatever? No. Yes. But not in the sea, not a salmon like that. Can't eat an insect. They do it because they need to refill their swim bladder. Because salmon and herring have an open swim bladder. They need to put water into their mouth, and when they swim down, they put kind of that water up into the swim bladder. There's this very tiny, small opening, just like a straw. If you don't have a surface, as illustrated here, the swim bladder fullness will go down. After 3 weeks, it's empty because it's leaking. And it's not a cod who can produce air to put into the swim bladder. It's the salmon. They have to have a surface. Of course, immediately as you give them surface again, they refill the swim bladders and everything is fine. But you can't have long-term production down there without having a surface where they can refill. Because then they become underbuoyant, so they will sink, and then they will have to swim faster, or they have to swim with an angle upwards. So Here's just a principle. Can we put in an air dome in these? So here's a principle drawing that we published some years ago. And then we made this. So this is a 3 meter. And it's 10 centimeters of air inside. And we needed a heavy weight to hold it. And here's you can see it. And this is for, of course, research purposes. And we sunk this down to 15 meters depth and kept the fish down there. And it went fine. So it can go well. But beware. The environment, what is the environment down there compared to up there? So this is done in a fjord, and we see that the surface fish, they were swimming on the top line here, and the submerged fish had to swim down here where the bottom line is. So the submerged fish, they were experiencing a lower temperature than the surface fish, so they were growing slower. Salinity-wise, they were well, in this fjord there was some brackish water, so they couldn't get to the brackish water, the one that was submerged. But the worst thing for us here was that at the end of the winter, they experienced rather low oxygen conditions. And these are the oxygen conditions measured outside the cages. It's even worse inside. So that was no good. So if you're going to do submergence, you need to measure the environment there and make sure that it's adequate for the fish. So there's a few commercial designs in use, using this already, and there's more coming. And you can be part of it. In the old days, this is a grønntveitmæren. In the old days, they used small cages. And then they started using bigger and bigger and bigger. How big can they be? This AB here refers to scientific observations of hypoxia. In today's present standard 160-meter cages, there is occasional hypoxia. In bigger cages, there is more hypoxia. In Ocean Farm 1, Morten Alvar and colleagues published a model and showed that there has been hypoxia there as well. So what decides how the oxygen conditions are? Okay, at the background level, the temperature, the water exchange, how many fish is there, number of fish, net flow in cages, and so on. And this is what the oxygen that the fish consume. So the black line here is the minimum they need to survive. And of course, it increases with temperature. And the white here is the maximum. If they're swimming as fast as they can, this is what they'll be using. So somewhere in between there, that's what they're using. Okay, so then you can calculate how much they're using. So looking at some designs here the water hits the front of this green, you've seen it before probably. And then the first cage is probably fine with oxygen, and the second one is kind of less and less and less oxygen here, because the flow goes through it. But they've done something so that they bring in water on the way, and so on. So they claim it's not too bad. But bear it in mind. How big can they be? Because there are limits. Normally, there are two limits. The appetite normally increases with temperature, and then the appetite, there's no effect on the appetite as the oxygen saturation is decreased, but there is a threshold for reduced appetite. And that threshold depends on temperature, and here's a list of what the threshold is. And if you go beyond the threshold for reduced appetite, you're into an area you shouldn't be for long periods, because if you reach the mortality of the time limit, then the fish will not survive. So that's when they are becoming anoxic. They don't have enough oxygen to produce energy. To sum up, salmon is a flexible, good swimmer. There are limits, but depend on size, temperature, diseases, time scale, and so on. Dampening, the water current can be dampened. How do they cope in waves? We don't really know, but it might go well. But you need room for them to swim down. Then that will make the trick. Or you need to submerge the whole thing. But then you need a air dome. Skirt, think about water exchange, oxygen, submerged cages with air dome might work. How large can cages be? We don't really know, but we can't just make them enormous. Thank you.
Thank you, Frode, for a super exciting lecture. We have room for questions, because, please.
A quick question. You're talking about some stress factors and limit states for the fish. But is there also another limit state for the fish related to the quality of the fish as food? You know, it's a similar way that you have with livestock, that if they're stressed out prior to, you can feel it in the quality.
Yeah, that's something you can discuss. So the quality in the cage, if they survive and thrive in the cages, the quality for harvest is normally not an issue. But if you stress the fish a lot on the way, then the quality is quickly reduced. So, but they can mitigate that by using cold water and stress them down before they are killed, and make sure that you cool them and so on. So they're just, yeah. So I wouldn't in the cage itself, as long as they have an adequate environment and so on, they are the quality is not made there. But it's up for discussions. There's not one answer.
All right, I think we shall move on so we don't spoil the time. So the next, thank you again, Frode.
Thank you. Hello.
Yes. The next speaker is, I may say, there is a different type of fatherships. You know, you could be biological father, you could be a PhD father, master father, and here is one of the fathers. Actually, he's my PhD father. So, Odd, please, the stage is yours, and the topic will be also now on education and research in aquaculture. What is important right now?
So, thank you, my son.
You're welcome.
And okay, so part of it is that I should talk about education. But, I mean, then I have got Paul Lader, who is the professor in aquaculture, to tell me what is available now of courses. There are 3 master courses here. And then actually it also names the other important persons here in the teaching, Arne Fredheim and Bjørn Egil Asbjørnslett. Then what is, I think, is I wouldn't say amazing, but it is very promising, the fact that there are so many Master of Science projects in aquaculture. And then, of course, this has happened quite recently. And then there's a program where you can combine aquaculture with other type of speciality. That means they are required to take a certain number of mandatory courses which deals with the aquaculture. That is good because then you get, I mean, there's so many different areas within aquaculture, you get then combined it. So it's offered in 10 study programs. Then there is a bachelor degree. Then this goes both on sea and land-based aquaculture facility. And then there's I think, a very good arrangement. That is that one tried to combine knowledge from high school, college, university, and also to industry. And there is several PhD studies involved in this, and I've been involved as a supervisor, and actually it goes back, I think my first PhD student was in 1991, that was Geir Løland, and then maybe I had the order of 10 PhD in this area. Then I will talk about some of the research which actually is part of these PhD studies, but also other area. One area is, of course, connected to that with water quality inside the net cage. And then what my first PhD student did in this area, that was Asgeir J, he studied the flow through net cases because it's important for what we have heard with the supply of oxygen. And then it's the cross flow that causes a turbulent wake that lowers the downstream velocity. And that, of course, restrict number of downstream cages, which we saw a discussion of in the last presentation of it. Now, then this formula, which is based on first principle, it gives a very good guidance, I think, on what is happening and can tell us. Then what is affecting this is things like net solidity ratio, marine growth, net deformation, and current speed. And of course the bottom weight is also an influence because of net deformation. An open question here is, which I don't have the answer to, that is to what extent do the fish matter of the flow. I mean, there are some reports that tells that it has an influence, but this has not been studied, I think. Then another aspect is that people may want to do computational fluid dynamics of this, and I have seen some attempt on doing it, and it is very hard to do it. That means we are back to actually what Lerland was doing. Then this is just an illustration. This is from SINTEF, showing that one is able to get a good picture of what are the current conditions, which is important for site selection. Then comes the effect of waves. And this is a movie from a fish farm and feed barge in the storm. And what you can see from that, which is typical of net cages, is that they follow the waves very much. But if you look at the feed barge, it doesn't follow it at all. And as you see illustrated here. So then what we have been working on is then ways of calculating wave and current induced response of net cages. This is an old picture, but of course there are other different arrangement of net cages. And it's very difficult to get all details here. So you must make some simplification. So because you want to simulate a whole sea state or many sea states, which prohibits, well, you should never say absolutely, but it makes it very difficult. Now, how we do the numerical modeling on net cage in waves, and this is based on work that has been done by different people. Here, one is Trygve Christiansen, and that is what we have is an equivalent truss model with the screen model for hydrodynamic loading. So we neglect details like knots and non-circular sections or twines, as you see here. Then we use Lerland's formula to find out what is the current, because that has an important effect on the loading on the net. What this type of formula neglect is the flow deviation due to netting, but the solidity ratios that one is operating with, that is not a big problem. Then there is a special modeling of the floaters, and then one solves time-dependent problems, which where you have a linear equation system for unknown tension. Now, something that this method then show is that you, in very severe sea states, will get snap loads in certain areas, which is a potential danger. And that is associated then with the relative motion between the floaters and the bottom weight. And I had a PhD student that studied this in idealized way in 2D in the tank. So, I mean, the danger is, of course, possible netting, damage, and fish escape. So here you see from the modal test, so start moving, and then you have a bottom weight, and then a net between, and then you will see at a certain position now, you get snap loads happening, which he measured then, and which he also calculated what was the consequences of. Then, based on this model that we have been working on, we can modeling then a complete net cage in irregular waves and current. And now this is for relatively high sea state, but I mean you can do anything, and it's long crested waves, and the net cage has a very small influence on the waves, which means actually what it means, for instance, if we're going to operate with a ROV at the net cage, that ROV is a very small structure, and it means it will move with the waves. And the same goes then for robots. So the consequence of all this is that the wave-induced motions, they have operational limitations due to that in reality. Then we have investigated in detail the mooring loads, and this is once more relatively high sea state with 4 meters. And I will just show the results. One thing that you can do with numerical method is that you can make different realizations, while that will be very cumbersome in experiments. Here is the anchor force, and this is the ratio between the anchor force and then the braking force. And you see there is not any problem there, but if you look at the brittle, the measurements in the brittle, then you have the same ratio. Then you see you get values which becomes much larger in reality. Then we also have studied wellboat at the net cage in waves and current. And I mean, the idea was to get out a basis for operational type of criteria. And of course, it can have different orientation relative, and we didn't see on the approach and when it left. So what is important here is that this is a coupled system, and you get similar you get with mooring of offshore structure, you get slow drift oscillations, and the contact between the vessel and the floater can have large influence on it. Then I mean, if one should set up certain type of operational limits, then it must be, for instance, related to mooring loads and stress distribution along the floater. And here is just shown an example on the calculations on the max stress in the 2 wave conditions, and then it's related to the yield stress. And as you see then at certain points, then you have going beyond that limit. Here is a project that this is an older PhD study, because I wanted to find out what influence does a fish has on mooring loads and net deformation, and then by doing modal test. Okay, so that means that you're operating with live fish in reality. And so we didn't have 100,000 salmon, but we had 800 live salmon. And they were occupying 2.5% of the cage volume. And Okay, so when you do model test, you don't have fish, I'm sure. And then is a question of what is the influence of fish on mooring loads. And here you see a side view that is in current. And now it depends, of course, on the current. It was the current you are simulating by towing the whole net cage with fish. And here you see they are ending up in the aft. That means they are blocking the flow through the net cage, which means you get higher loads acting. So now it's the question of the waves. They have also done the waves. And what happened then is that they went down. So which then, well, this is, I think this is very important of other reasons. I mean, what, can we set up some simple way of telling a certain type of criterion as we have in operational studies of a ship, for instance? So some of the fish went down. I mean, when it comes to the mooring loads, we talked about 10 to 27% of it. Okay, so that is modal test. And then the question is, there was also done without, I mean, rigid modal. It has no influence on it. But the problem here is this correct to do? I mean, what we do in modal testing is that we fruit scale everything, okay? But the question is, we don't scale the behavior of the fish. And does the fish behave similar in that towing tank than it does in reality? That is, of course, an important question. So therefore, the last presenter, it is important to get knowledge transfer on thing here. And it's also related to this with the fish going down, is a question of criteria for fish comfort in waves. I mean, we have criteria for human beings, which is well established, but do they apply for the salmon? I don't know. Then we come to the closed fish cages, which are proposed to avoid salmon lice. And this is just showing one design, and the water exchange is needed. Then here come the problem of sloshing. I mean, that means resonant water motion inside them. And here you see from experiments what I mean, where you have swirling. I mean, you have your cup of coffee, and you can see, you can get similar type of picture. And now, this is of course an idealized situation. You must take it together with the whole object operating in wind. So this with waves like that, this was a major concern when it was the development of spherical LNG tanks. So that goes long back in time, and is also a problem related to new type of LNG tanks. So here is a picture of different types of it, and I want to get into the picture of hydroelasticity. That means basically that we have a mutual interaction between structural deformation and hydrodynamic loading. And then we have the different types of structures: flexible, semi-flexible, and rigid. And I had a PhD student together with Asgeir, and she set up a numerical model. It was idealized, but then you saw that snap loads can easily become a problem in flexible cages in reality. So then we want to do model test, which is giving us a lot of information, but it's very challenging to scale model test where we have this hydroelastic effect, that the structure does not behave like the rigid. Then also, when one is doing model test, one often do it with one model. But if you have an arrangement like it's shown here, you will have a strong hydrodynamic interaction between them. Then here is from experiments. This is with hydroelasticity. It was a semi-flexible cage, and it shows the effect of a so-called overlying structural molding. And what you now see inside is that it increases in magnitude, and then you see a tendency that the water is going around here. And what is very important here for this resonance to happening, that is that there is a closeness between natural sloshing period and also what the wet overlying structural natural period is. And this was for sure the case in this case. And we can avoid this violent sloshing then by higher structural stiffness. It's a question of finding natural period. And we can also avoid it by having small internal free surface dimension, which I believe is part of this structure. But I have not been inside it, so I don't know. But I've seen some picture of it. So you can play around with different things like that. Then something which we noticed in analyzing experiments, that is the floaters. That is, it depends on the sea condition, but they can go in and out of the water, as you see illustrated here. And the consequence of that, they go in and out of the water, is that you get mean sinkage and also a mean heel, which is not desirable. And in extreme cases, you can get dynamic instabilities. So, I mean, general guidance is then that one should try to avoid floating color with small cross-sectional radians. Then you have this with lice skirt, where this is some study done by David Christiansen, and found out that there was very poor water exchange with less oxygen for the fish in the upper layer. And then we have the Salma thing going to the open ocean, and these have been tested in the model basin by Marintekniske, and I saw some of them, and it looked very good what I saw. But of course, it's a question if there are something that can cause surprises. So basically, here we have a good example on transfer of knowledge from offshore engineering, and so. One thing which I asked myself about when the tests were done, that is, does wave slamming impact of steep waves matter? And it was told to me that it was not a problem. But so basically, we don't want things like this to happen, which is an offshore structure. This is an accidental load case where you get extreme loading caused by that. There's also another accidental case by Jørgen Amdahl, where he has studied the fact that you have a wellboat and for vessel speed 3.6 meters per second, and this could, for instance, be a ship length of about 80 meters, which is not unrealistic, I think, for that area. So then some concluding remarks. Then about this, it's a question about towards the ocean with fish farms. I think we need more knowledge about fish behavior. And then we have implicitly type of further marine technology studies that can be used. And then you have this new dimension, which I guess they have been talked about many years, but recently there have been a report that there's a large potential for growing algae in Norwegian water. So, thank you.
Thank you all. Thank you.
Yeah.
I think there is going to be a panel debate, and Sverre will chair that. So, Sverre, who should... Odd, you are supposed to be there.
We would like to invite the speakers of this session to come up on stage, or remain on stage, Odd, please, if you're... so that we can have a bit of discussion between you and also with the audience. I think so the presentations that we've heard now in this session, they have circled around the interaction between the fish, the biology, the life, and the technology, and that is something that is bit particular for aquaculture when it comes to marine technology. That's much less of a concern in offshore, of course, and shipping and so on and so forth, although there are, of course, interactions there as well. So we need to know how to do technology on the premises of biology, as Bjørn Egil used to say. So it's of interest to hear your view on when it comes to the environment that we subject the fish to through our aquaculture. What do we know? And I think Frode has told us quite a bit about that. And what do we need to know? What is the knowledge gap that we need to fill in order to enable, say, sustainable aquaculture that is treating the fish well, so that it can thrive and survive until it's ready for the slaughter. So, what are the knowledge gaps in this area? What do we know enough about what the fish can endure and not endure?
Should I start?
Maybe, yeah.
Yeah. So from my talk, it's kind of how do oxygen go through the cages and how is it depleted? So that can be modeled. Someone has tried, but not well enough. So someone should do that much better and find the kind of critical values. So and taking in the variability. So far they kind of used one number for what the oxygen consumption is, and so on. So that can be done much better. And in that context, why don't you design several smaller cages instead of one huge one? So that there's a knowledge gap there. Yeah. And then it's all about the waves, but so that's more like my input at first. Was that on? Yeah, yeah, that's better. Yeah, okay. So I'll give the word to you. Yeah.
Okay. Oh, I mean, I touched upon it. For me, it's a question is, what is the criteria for fish conform? I mean, you talked about seasickness. I mean, normally then we talk about explorations. So then, is that behind it? If it's the level of exploration is imposed, and then it's a question of setting a certain limit, as you do for human beings in different type of context. So the first lacking thing is exploration the proper thing? So then the next thing is to set up a level, and then you can do estimates of that for the different types of fish cages that you have. You can calculate it. Yes, and then you can see, for instance, to how large sea states can you operate. But there's a missing point here, as I said. That is exploration. Is that the basis for it or not? Yeah.
So,
yeah. I just want to comment because there is a lot of empirical data.
Yeah.
For the most exposed sites, both for kind of stiff structures like the SalMar offshore platform on the kind of the fish behavior in exposed environment, Frode. And for kind of our technology, as you also spoke about, Odd, on the kind of flexible cages. As I said, we are operating in I think it's like 5 to 10 sites where we have between HS4 and HS6, where we also have experienced those conditions. And what we see is that the kind of the fish behavior is no problem on these sites. And what they also say is that the quality of the fish on the more exposed sites is excellent, Frode. And that was also a question that you got on the quality of the fish from Kjetil. And I guess that's the taste of it or something. But the two aspects: the quality of the fish is excellent on exposed sites, and also the less dead fish amount what we see on the most exposed site when you have a 200-meter cage with about 150 to 180,000 fish.
Yeah, so then you can discuss what is the reason. Is it the environment, the better environment in these more exposed cages?
I think it's the quality of the cage.
But just take what Odd says a bit further. So we're part of this green platform that looks at sustainable offshore farming, and in there we're going to put fish into conditions that looks like waves. So we're going to make them experience fluctuating water flows, so accelerations. Yeah. We're going to make waves in the tanks. We can't make them 150 meters long, but we'll make wave conditions, and then we will also make pressure changes. Well, that could be an obstacle as well. If the fish is swimming as the waves go, they could experience to be under at the bottom of a wave and under the top of the wave, and then they can experience pressure differences of maybe 5 to 10 meters. And if they're doing that high up, what's the impact? That means that the swim bladder will go like this, like a balloon that is half the size and full size and half the size and full size. What's the effect of that on the fish? Of course, the simplest would be if there's room for them down there and they swim down there. But we don't know that yet. Yeah, so yeah, we're going into this, but ask me again in 3 years' time.
And we've also heard rumors of transportations in wellboats where the wellboat has been in severe weather, and on arrival, all the fish are dead. So that's an indication that motions where they cannot escape, for sure, can be really, really dangerous for the fish. And this is important to know more about for the design of wellboats, and also for to restrict their operation. You might think that you should have weather limits for the operation of the wellboat if we can establish such a relation between the sea state and the motion of the ship and the health of the fish. So I think we need to know more about this.
Yeah, so clearly, is that because of the sloshing effect of the water inside the wellboats, or is it because of the movement of the wellboat and the water itself?
Good question. We don't know.
But the bottom line is that the fish experience a certain acceleration. I mean, that is the bottom line. I mean, it can be, of course, more violent if you have sloshing, and it means also implicitly that if you are, I would guess that if you are on a closed cage, maybe you are more severe. But the bottom line, it is what the fish is feeling. If the problem is related to what you say, that it feels this with the pressure, it's very sensitive to the pressure, or what? I don't know. Okay, but anyway, I think what is important is to have that information going across, because this will be a clear limitation for the type of structure you're gonna design. No doubt about that. Yeah.
And we would try to do it in small scale, but that's not always realistic. But they will make numbers that we can use, and the best would, of course, to be out there and see. But we are not out there yet.
No. I think that's fine. What you say? Yeah.
Is there any questions from the audience to the panel here? Yes.
Should I just take it by voice naturally? Will that suit?
I think so, yes. That's,
it's clearly that we have been working with fish in wellboats for 30, 40 years, and we just say it will get seasick, and we just don't exactly know what is actually going on. So I support that. From the lecture of Martin, we learned that he is running a 200,000 fish in a 200-meter surface net pen, and he's only been doing that up to 6 to 7 HS. Well, we have larger also other places, as you know, in Tasmania, where you've also been working. Now I will take you out and say, we will produce fish in about 3 million fish. Not in 200,000 cubic meters, but in not in 70,000 cubic meters, but in 760,000 cubic meters. Now I'm talking offshore. And now I'm talking saying that we are 61 meters deep in this smart fish farm. And my question goes then to Frode. I will be out there, and we will have the first 10-meter HS with a wavelength of 150 meters, which means you have to go 75 meters deep to get some.
To get no more, yeah.
And then my question is, how many hours will my salmon survive in that condition until it gets picky and goes right into the net pack? And as you know, I'm a veterinarian, been working with this industry since 85 or something. I've seen many things coming up. And now I want to have you answer this, because you are the main expert in Norway on this. Why not now? Please.
Well, the answer is, of course, that I don't know, because we haven't done it yet. But so there's the wave action that we don't know of. If they go down to 60 meters, fine, they might be okay. They'll probably be okay if they go down. But is there room for everyone there? No, is my immediate answer. So, and then the design. You know we have given input on this before. So this is there's too many fish.
Directly is that death is one thing that we use as a welfare indicator. That's not a good one. But for how many hours will this fish suffer until it gets fated? For how many hours, how will this fish be able to live there? 3 million out there. We're spending close to between 2.5 and 3 billion NOK on building this. But where the hell will this fish survive?
I don't know, and you don't know, and we don't know. And we should be careful. Maybe we shouldn't try out with that many fish. We should try with less fish at first. And as I said at start here, maybe we shouldn't try it out in these enormous cages. We should make several smaller ones instead. But we don't know, and then but we need more knowledge, more models, and we need to test out, and we need to see. And we need what's the impact of the acceleration, as Odd points out here, very clearly. We don't know that. We know that in the open sea, salmon survive and thrive, but then they are few at a time, and they can go wherever they want. There's publications showing that they go to 500 to 1,200 meters depth, so they can go deep. That's not a problem.
okay, last question goes to Reza. Sorry.
So you said 10-second wave, right? So it's 150 meters long, but the velocity under the wave is changing exponentially. So if you go down to 75, it's 0. But perhaps we can take, I don't know, 2 meters per second. So you don't have to go that far down. So maybe you're looking at 40 meters. So you have to look at that profile. Because the profile is going from this like exponential, very close to the surface, the velocity is very high. If you're 10 meters below, it's much less. It's e to the power of kz minus kz. It might be get closer to the surface.
That is a good point.
Yeah. So it's good to have the hydrodynamics on board. Thank you very much. Yes, Nere, is that very quick?
know nothing about aquaculture. I'm named architect. And I heard this huge experiments with 3 billion of NOx, 1 million of fish put into an environment, and you don't know what's happening. I cannot understand that this is low. Where is the legislation? Where are the requirements for fish behavior, for safety? Because if 1 million fish start to escape, it will be a catastrophe. And what do you mean about this lack of legislation, or lack of rules and regulations on this development?
That's not a small question, but is there a quick intermediate answer, or else we might need to let it hang in the air?
So just a comment to that, because there is a requirement for the authorities at Mattilsynet in Norway, where you have to do this stepwise. So you have to do it stepwise to put more and more fish out in the cage, which we also have done in the kind of flexible cages and development licenses. So there is a system for that. They won't put like 4 million the first time. So there is a system for that. I don't remember the paragraph, but there is a system.
That's good. Thank you very much, and thank the speakers and panelists. So we are getting close to the end of this issue of the Marine Technology Days. It has been really good to have this physical gathering of experts and industry and students and staff to get together and discuss important and relevant topics. I must say that, well, I'm not unbiased here, but I'm quite happy with how this program has evolved. I think that we've had 2 interesting days with lots of good information. We started off yesterday with the challenge of greening shipping and creating zero-emission shipping, which my takeaway was that, well, it's possible, but we are running late, and it's really time to scale up. So scale up the action, not just the talking. There has been lots of talking and not so much action, and that has to change if one is going to meet the deadlines and objectives that has been set. And we also learned the enormous scale of the renewable energy that we will need in order to do this. Which it's an open question where that energy is going to come from. We then learned about offshore renewable energy from wind primarily, but also solar, and I think we learned that again, it's possible to scale up in the pace that is planned, but also that it is extremely challenging, and that the amount of hardware that is going into this is enormous, and is even enormous compared to the offshore oil and gas infrastructure that we have become quite familiar with. So it's really a huge task to install and fabricate and install all these wind turbines and other related structures. So again, it is challenging. But as was pointed out yesterday, this also means that there are plenty of opportunities for us as industry and as university and academia and researchers and so on. So it's clear that we're needed, and that's good. I think we should view this as a challenge and try to see the opportunities and try to be part of the solution, and not just sit on the sideline and worry about the problems, even if they are numerous. So today, first we had an update on autonomy in the marine sector with Asgeir and AMOS and Beate telling us about the great new infrastructure that we are installing in the Trondheim fjord, and we heard about Seabus, which is one of the latest spin-offs from NTNU in this field, and also about how subsea robotics can improve both the offshore oil and gas, but also offshore renewables in terms of making things more safer and efficient, and also reducing emissions. And lastly, we have gotten an update on the fascinating interaction between technology and biology in the aquaculture sector, and that makes me curious and wanting to do more in this area. So we'll see what we can develop in this area. It has been a fairly wide range of topics, but I think it has been a very good experience, and I'm sure that we are going to do this again. We have taken up the tradition, so this will not be a one-off, but we will come back. Don't dare to tell Live that when we will come back with it, because I think she has had some really tough days, both leading up to this and also through these 2 days. But we are going to come back in not too long with another issue of the Marine Technology Days. And in the meantime, we are more than happy to hear from you what could be good topics for such a seminar. And in general, the purpose of the Marine Technology Days is to keep and develop the contacts between the industry and our former students, which are now out there doing all the good work, and us here in the department, because this interaction is crucial, both in order to develop our studies, to keep them relevant, to get good topics for master theses and PhDs, and also to establish research projects. We are doing applied research, and without close cooperation with our users, it will not be relevant, and then it is completely useless. So this contact is crucial, and this is one way to develop it and maintain it. But there are also many other ways, for instance, through collaboration on master topics, and as I mentioned, the research projects. So you should know that our door is open, and our email boxes are, there are always room for more messages from you, and we hope to hear from you more frequently. We're also going to take up our industry collaboration arrangement called Samarbeidsforum Marin. So those of you who have been missing messages from them, you will get one shortly, because that's another way to have a collaboration between the industry, the takers of the students that we educate, and the department. So we come back to that. So I'd like to thank all the speakers for giving very good presentations, mostly on time, particularly today. A bit sorry about the delay yesterday, so we are learning, but I think it ended out okay. And thank you to the chairman, to the organizers, also the technical organizers, which have done a great job. So I think we should give them all a big hand of applause. And there are also some practical information. So now there shall be some light lunch served outside. I'm possibly similar to yesterday, I don't know. At least something to eat. And then in 15 minutes, we will have a ceremony which is not directly related to the Marine Technology Days, but rather to the Ocean Space Center, where there will be a unwrapping of a physical model of the new center, and there will be some speakers and stuff, and there will also be cake. And I'm told that there will be a lot of cake. So there will be for everybody. So please stay around for that also if you have time. And then for those that are staying even longer, we have MIT is putting up a review here this afternoon. It is starting at 6, right? Doors open 5:30. So those who have registered for that, please stay for that, and there might also be some free tickets. So if you don't have a ticket but really want to go, contact us. 10 free tickets. So that's an option. So also to the audience, thank you very much for your kind attention and patience, and have a good day.
Man sier at bak skyene himmelen alltid blå. Bekymringsløs og full av muligheter. Men ønsker du muligheter, trenger du ikke se opp. Du kan se utover, mot havet. Havet kan løse mange utfordringer, men løsningene kommer ikke av seg selv. Vi trenger kloke hoder som kan utvikle miljøvennlig skipsfart, fornybar energi, undervannsroboter og løsninger for matproduksjon til havs. Her på Marintekniske ved NTNU får du et unikt studiemiljø hvor du kombinerer teori og praktiske oppgaver, møter verdensledende forelesere og får venner for livet i en samlet og sosial campus. Når du ferdig, vil det være mange muligheter til å jobbe i Norge og internasjonalt, og å få videreutvikle dine ferdigheter. Med en marin utdanning får du en blå himmel og et hav av muligheter.